Hello, my name is Ryan, and today my group and I will be giving a presentation on our final project for CS4435/9644, which is a survey of selected distributed NoSQL databases. So the databases that we'll be covering include Elasticsearch, MongoDB, CosmosDB, and CacheDB. So the first one is Elasticsearch. What is Elasticsearch? Elasticsearch is a distributed open source NoSQL database that supports structured, unstructured, textual, numerical, and geospatial data. Its primary focus is near real-time search capabilities. Common applications of Elasticsearch include document searching, email searching, product searching, and log data searching. So how does Elasticsearch work? Elasticsearch can take in unstructured data from multiple sources and indexes and stores the data, where the data is stored in JSON documents and acts as the main and basic unit of information in Elasticsearch. The primary data structure in Elasticsearch is called an inverted index. An inverted index is a mapping of each unique word to each word's location within each stored document. The index makes it possible to quickly locate documents with any given keywords. The index is stored in either one or several partitions. These partitions are called shards. A shard is a subset of an index where Elasticsearch creates these shards when the volume of data stored in a cluster exceeds the limits of the server, therefore splitting the index into smaller pieces, called shards, across several servers. A node is a single instance of an Elasticsearch process. It is a server that stores data and is a part of the cluster's indexing and searching functions. Nodes discover each other in the cluster by their shared cluster name. Elasticsearch will create, replicate, and distribute shards dynamically to the various nodes within a cluster as needed. In an Elasticsearch database, each shard has multiple copies, where one is referred to as a primary node and the other shards are referred to as replicas. When data is written to the index, it is first written to the primary shard and then synchronized with the replica shards. Both the primary shard and replica shards accept read requests. In order to maintain consensus across the nodes, Elasticsearch implements its own consensus system called Zen Discovery. For management of concurrent requests, Elasticsearch uses optimistic concurrency control to ensure that newer versions of documents are not overwritten by older versions. To maintain consistency during write operations, Elasticsearch supports consistency levels that allow a preliminary check to see how many shards are available for the write to be permissible. To maintain consistency during read operations, new documents are not available for search until after the refresh interval. Some of the advantages of Elasticsearch are as follows. Near real-time search capabilities. Its distributed architecture makes it possible to search and analyze huge volumes of data in near real time. Documents stored in Elasticsearch are distributed across different containers called shards, which are duplicated to provide redundant copies of the data in case of hardware failure. The distributed nature of Elasticsearch allows it to scale out to hundreds or even thousands of servers and handle petabytes of data. Easy integration within what's called the ELK stack is also a selling feature that allows for simple data ingestion, visualization, and reporting, and this is a very common use case for Elasticsearch. Some of the disadvantages include the fact that Elasticsearch can sometimes suffer from a problem called split brain. In a cluster, there is one active master which updates and controls the cluster-wide state and operations. Elasticsearch can suffer from the problem of split brain where, in case of a network partition, a node can think that the master is dead and elect itself as a master, resulting in a cluster with multiple masters. Also, the expertise required to know how to scale up Elasticsearch to large-scale, enterprise-level usage is not trivial. There are other database tools that are easier to scale up out of the box. While Elasticsearch can technically handle massive datasets, other database tools such as MongoDB generally perform better for such use cases. So next database we'll talk about is MongoDB.
What is MongoDB? MongoDB is a distributed open-source NoSQL database with a document data model. The documents are BSON files, where BSON is a binary encoded serialization of JSON with more data types. MongoDB has a flexible schema. This means that the documents do not have to follow a schema, and MongoDB accepts any BSON documents into a collection. Some applications of MongoDB include product catalogs for e-commerce websites, data analysis, video games, and archiving. So how MongoDB works. The JSON documents in MongoDB are composed of key value pairs where each document has a primary key for indexing. The primary key is automatically generated by default or can be defined by a provided schema. Secondary keys are able to be created to speed up queries. Documents are grouped into collections defined by the database architect and can interface into a wide variety of applications as shown in the diagram. For consistency models and replication in MongoDB, each replica set has a primary node that confirms all write operations. Read operations can be sent to any replica node. Read operations can be sent to multiple replicas to speed up queries. All operations on the primary node are mirrored to the secondary nodes. Collections are self-contained, so databases can scale with replication very easily. MongoDB replica sets maintain the same dataset, and having replicas working with the same dataset provides redundancy and high availability in the case of failure. When the primary node does not communicate with the other nodes for a greater time than the timeout period, any eligible node can call for an election to nominate itself as the new primary node. During the election, no write operations can be performed, ensuring consistency in the case of failure. The advantages of MongoDB: no fixed schema, it can be run anywhere. Most collection architecture supports horizontal scaling out of the box. MongoDB was designed with replication and high availability in mind. MongoDB provides native drivers and SDKs for many popular programming languages. Disadvantages of MongoDB: there's no join operation supported on the database side, and the programmer must resolve them on the client or the server. To achieve a good performance with MongoDB for a large data set, proper queries utilizing indexing is required. Document size is limited to 16 megabytes.
CosmosDB is a NoSQL proprietary multi-model database for large-scale data management. Schema agnostic and focuses on being planet-scale data management solution with fast multi-region read and write latencies globally. There's API integration, which includes SQL, MongoDB, CacheDB, Gremlin, and more. Also provides users with various levels of consistency and control over region locality for replicas. CosmosDB works by storing items within containers, which are then grouped together to form databases. And from your database account, you're able to view these in different forms based on the API that you may have chosen, may have access to see these items and containers. The consistency models for CosmosDB, well, there are 5 of them. The top one focuses on real-time synchronous replication to prevent any data loss. And as a result, it has increased latency and the lowest performance, but it makes it great for financial transactions. The second level, bounded staleness, scales things down, focuses on asynchronous replication, but has a predetermined staleness window. This can be configured based on number of writes or a period of time before the data is synchronized. The middle tier, session, focuses on an application session and keeping that session up to date. Interestingly, this is the default selection when you create a CosmosDB account. Consistent prefix, the second to last level, similar to the second tier, it ensures writes are performed in order, but does not have that time lag guarantee. Finally, eventual consistency. Well, this is the basic model. Provides users with consistent reads. They be replicated at some point and does not guarantee order of data. As you can see here, these are some advantages of CosmosDB. Most significantly, the first one, provides options for companies to consolidate data in one place instead of using multiple databases. And it does this through the use of APIs as well as different representations of data. Some of the disadvantages for Cosmos, most significantly here, would be the subscription-based service. So if you're trying to switch to something different, it's not ideal.
What is CouchDB? CouchDB is a peer-based distributed NoSQL database that uses JSON to store data and uses JavaScript and HTTP to index and run queries. Since it uses very web-friendly languages, this database works well online and even on mobile devices. Common applications of CouchDB include database applications for mobile devices such as iOS and Android devices, IoT sensor data management, comment to reply sections on blogs, and service logs. How does CouchDB work? The architecture of CouchDB is illustrated here. An HTTP request is written in JavaScript that allows creating ad hoc views made of MapReduce jobs, and these requests are used to create indices and extract data from documents. The CouchDB engine is based on a B+ tree where data is accessed by keys or key ranges which map directly to the underlying B+ tree operations. It is the core of the system which manages to store internal documents, data, and views. The replica databases are used for replicating data to a local or remote database and synchronizing documents. In terms of consistency model and replica maintenance, CouchDB keeps track of updates by giving each change a sequence number. This number is used to track changes between any sequence number until the current time, which can be used to create a list of all new and changed documents to send as an update. If a request fails, the database will be left in an inconsistent state and wait until a request is triggered again to continue updating. CouchDB allows the user to select the number of shards and replicas they wish to have for the database. The user can also see the number of nodes that are allowed to be down at any given time while still remaining functional. Bidirectional replication is also supported in CouchDB such that changes made to replicas will update the original database as well. When CouchDB attempts to replicate a database, it will compare documents on both sides. In the case of a conflict, a deterministic algorithm is run to pick which revisions is kept on both sides. Due to the deterministic nature of the algorithm, both databases will use the same change and stay in a consistent state. Some of the advantages of CouchDB are listed out here as follows. The database can be replicated to other devices and used offline. It is also designed to be very easy to understand and use. Bidirectional replication means that changes on the replicas will modify and update other replicas. It features very fast indexing and retrieval, and access to previous versions of a document are possible due to the sequence numbers. Some of the disadvantages of CouchDB are as follows. It uses typically more overhead storage than other databases. Temporary views it generates can be slower in performance, and conflicts can happen in the context of offline usage. It also does not support transactions. Thank you for your time, and that concludes our presentation.